Hi, I'm Mason Vale from Boise State University, and in this video we're going to talk about black box testing of an abstract data type as defined in an interface. For nearly any abstract data type, or ADT, the number of possible combinations and sequences of method calls that could interact with or change an object of the ADT type is effectively infinite, so it's not possible to exhaustively test every imaginable scenario. At the same time, as a programmer, we need to be confident that the implementations we're writing will work the way that the user expects before we trust it in a production environment. So we need a way to build confidence in our implementations. By carefully planning and developing a robust suite of tests for critical and representative changes to the ADT using its interface-defined methods, we can reduce the risk that there are flaws in the implementation. For every individual change scenario that we identify, we need to test every interface method using both valid and invalid inputs where appropriate to confirm that every method is behaving consistently with the expected current state of the list according to the ADT documentation. It's the combination of all tests returning results consistent with the ADT for all change scenarios that builds confidence. This approach to working exclusively through ADT methods and the ADT's described mental model is called black box testing. It's all about the ADT and it makes no assumptions about any particular implementation. So a note on terminology. A possible change to the ADT is most commonly referred to as a test case, but I'm using the term change scenario in an attempt to clearly distinguish between the concept of the test case and an individual test. We start building a test suite from the simplest possible change scenarios, and we only move up in a stepwise fashion to more complex scenarios. If I were testing a list, I couldn't begin with a multiple element list if I haven't first established that I can correctly build up to that multiple element list. It bears repeating, it's the combined results of all tests of all methods returning consistent and expected results for all change scenarios that's building our confidence that the implementation is working correctly. No one change scenario and no individual test is trustworthy on its own. Since we can't exhaustively test all possible test cases, we need to identify critical, high-value, high-risk test cases and then representative test cases or scenarios. So high-risk test cases or critical test cases mark really significant transitions or boundary kind of conditions. For example, when I first initialize a brand new data structure, or I add the very first element to an empty data structure, or I remove the only remaining element from a data structure. Anything that involves boundaries such as beginning or end of a list, or significant values like the last valid index at the beginning or the end of a linear data structure, or the first boundary, the first index that would be out of bounds at either end. These would be high value, high risk test cases that should be included in any good test suite. But we also then have test cases that represent a broad category of similar test cases, similar scenarios. For example, if I have a list can be any length. If I've already established that I can add an element to the middle of a relatively long list, there's no real benefit to testing to make sure that I can add to the middle of a slightly longer or slightly shorter list. I would consider my one scenario to be representative of adding to the middle of any long list. So those serve as equivalence cases. I have one test case that's representing many other test cases. So how do we go about identifying appropriate change scenarios, test cases, and their associated tests? Well, let's look at a very simple ADT. This SuperSimpleSet ADT is representing kind of the concept of a mathematical set, a collection of unique elements. So I would define this ADT in an interface similar to what we see here, and this interface includes very brief documentation, but it's adequate for our purposes. We see that the overall idea of the SuperSimpleSet ADT is that it is a collection of unique elements. then each of the three methods that make up this abstract data type includes its own specific Java doc that describes what to expect from that method. There is an add method that takes in a new element, and according to its description, it adds the given element if it's not already in the set, and it has no effect if it's a duplicate element. So I already see that we're enforcing the overall concept of unique elements. So there's nothing here that says that there's an error or an exception that takes place if I try to add a duplicate element, but I'm told that this method will add the element if it is a unique new element, and it will not add the element if it's a duplicate element. I'm also told that I'm supposed to pass in an element to add as the input parameter to this method. So I know what to expect from the add method. I also have a contains method that takes in an element reference. And according to the documentation, this contains method should return true if the element is in the set, else it should return false. So I should be able to pass in any element reference, and if it is in the set currently, I expect a true value, and if it's not in this set, I expect a false. So I know what to expect from this method. The third method is always supposed to represent the current size of the set, the number of unique elements in the set. So it should be returning an integer value reflecting the current size of the set. So with this ADT defined in an interface, I now understand the mental model of the set concept, the SuperSimpleSet concept, and I know what to expect from each of the three methods. Even with only having three methods and only the add method actually changes set contents, we still have several change scenarios that we need to explore. Each one of these change scenarios is represented by a starting state, the single change to the set, and an expected resulting state. So a starting state, a single change, and an expected resulting state. So we have to start at the very beginning with our simplest possible scenario. So we need to start by initializing a brand new superset object, SuperSimpleSet object, which is a critical boundary case. We want to know if I had no set and I call the constructor, do I get a correctly initialized brand new empty set? To confirm this, we'll add tests for each one of the SuperSimpleSet ADT methods that begins with this change scenario. I begin with a newly instantiated set object, and I call the method to confirm that the method returns a result that's consistent with a brand new correctly initialized set. So this very first change scenario would look like this. I have a starting state of no set. There is no set. My change is that I call the constructor for the SuperSimpleSet object, and I expect that the result is I have a new empty set. So my starting state was no set, my one change was calling the constructor, and my expected result is that I have a correctly initialized brand new empty set. These are my tests for the ADT methods to confirm that my change scenario is working correctly, that my constructor correctly initialized the brand new empty set. So if I have an empty set, I should be able to call the add method and pass in some new value. And I expect, as a result, no exception to be thrown. You might expect that I'm going to check the contents of my set after this, but we're going to build our way up one step at a time to actually confirm that the add got that original element in there. Right now, my expected result from calling the add method is that it does not blow up in my face. I get no exception thrown. I should be allowed to call the add method with some value. I also should be able to confirm that if I pass in a value to the contains method, because the set is empty, contains should return false for any value that I pass in. So I need to be able to add some element that doesn't exist in the set with no exception. I also need to confirm that no matter what I pass in to the contains method, it should return false. The size of a correctly initialized brand new empty set is 0. So I'd better get a 0 back when I call the size method. So these are 3 tests for my change scenario that help me confirm that I correctly initialized a brand new empty set. Note that even though I've been building confidence that I've correctly initialized a brand new empty set, these tests don't prove to me that I've correctly initialized an empty set. It would be possible that I could have an add method with no code in it whatsoever that never throws an exception, and so it appears to pass this test even though it didn't actually add element A to my set. Likewise, my contains method could always return false, so it appears to be passing but it really doesn't work, and size might always return 0. So you can get false positives from a test that makes something appear to be working, but until I go on and continue to test, I can't say that I correctly initialized an empty set. We need more tests in order to build our confidence. Assuming that I have correctly initialized an empty set, my next possible change that I could make to this abstract data type is to add the very first element to the empty set. So my second change scenario after the initialization scenario is to assume that I'm beginning with a brand new empty set. I can call the add method with a new element, and my expected result is that I have a set containing that element. So my beginning state assumes I had an empty set. My one change is to add an element to the set, and my expected result is that the set now contains that element and that element only. So tests for this scenario, I have more possible tests, because now I have the possibility of adding a duplicate value, I have the possibility of adding a new value, I have the possibility of checking that I contain the value I expect, and I have the possibility of checking for contains with an element that's not in the set. So I have more tests for this scenario than I had for the first scenario. I should be allowed, according to the add description, I should be able to call add A again without it resulting in an exception. I don't expect the duplicate value to be added to my set, but I also don't expect an exception as the result. I also expect that if I have a set containing A, I should be allowed to call add with a different element, something that wasn't in the set already. And again, I don't expect an exception as a result. Contains A is the first place where I'm actually going to confirm that that original change, the adding the A from our previous scenario, actually did work. Because now that add A is the change that I'm testing. I'm testing that add A actually successfully got me from an empty set to a set containing A. So contains A is now expected to return true. But I also double check and make sure that if I pass in a value that is not expected to be in the set, those should still return false. So I'm testing that the only value that's in my set should return true, and a representative non-set element will return false. If I do have a set containing one element, the size method should return 1. From a set containing a single element, I now have two possibilities for add methods. We had an add method that tried to add a duplicate, and we had an add method that tried to add a new value. So each of those represents another change scenario that I need to test. So if I have a set that already contains element A, and I call add with that same element A, I expect that the set at the end is still the set containing 1A, because sets only contain unique elements. If I add A to a set that already contains A, the set still simply contains A. So I have the same 4 tests and the same 4 test results that I had in the previous scenario, because my end result was the same. I still expect that my set after this change scenario contains only element A. So I have the same tests and I have the same expected results. But what I've confirmed is that by adding A, a duplicate A, my size has not increased, but I still recognize that A is in the set, B is not in the set, and I can call my add methods again. Assuming that I have a set containing only element A, as before, we also had the add a new element B as a possibility. So if I have a set containing A and I add something that's not already in the set, I expect the result to be that the set now contains A and B. Both of those are now elements in my set. So my number of possible method tests has grown again. I expect that I should be able to add a duplicate A without exception, I should be able to add a duplicate B without exception, and I should be able to add something new without any exception being thrown. I still expect no exceptions from any call to add. My contains A is still true, my contains B should now be true, and if I try to call contains with something that's not A or B, I expect a result of false. I also expect that the size of this set is now 2. 2 unique elements are in my set. At this point, we've defined 4 change scenarios for our abstract data type that cover most of our boundary cases. So I feel confident at this point that a new set would be correctly initialized. I feel confident that the first element could be added to an empty set. I feel confident that add only adds unique new elements. And I feel confident that contains accurately reports on the contents of the set, and I feel confident that size is being accurately reported. I can continue adding new scenarios for larger sets, but I'm going to start to see diminishing returns on my efforts. I won't be learning anything really new. So how far do we go? When can we stop? Well, every novel new test case or test will reduce the risk that you've missed something. No truly novel test is worthless. However, we've already established that we can't exhaustively test everything, so we have to decide when to stop. Well, all boundary cases are critical. They represent something important. They represent a high-risk condition. All boundary cases need to be tested. We also need equivalence cases for any anticipated general categories of changing. We need something to represent all of the usual ways that we might modify a particular data structure. So as new scenarios are added, if they're conceptually overlapping existing equivalence cases, we're going to start to see diminishing returns. You are eliminating less risk with new scenarios that overlap old scenarios than you did with the high-value boundary cases and with the first version of an equivalence case. So at some point, you will have to decide that any remaining risk is acceptable. You can live with the remaining possibility that you've missed something, and you recognize that adding additional test cases may not be a useful use of your time. That decision is generally up to you as the programmer. It can be that time has run out, but in general, it's when have you decided that you can accept any remaining risk. You've eliminated all of the most dangerous scenarios, and you can accept that there's a possibility that the next test might have revealed something. So just one last time, we can never say that we have proven or guaranteed bug-free code, but we can reach a point where we can honestly say, I've thoroughly tested this code and it passes all tests, so I'm confident that it's production worthy. The best time to design and develop a test suite for an abstract data type is before you write a single line of implementation code. And there are several reasons for this. It forces you to understand the abstract data type and all of its methods before you start writing your code, or more accurately hacking at your code because you don't really know what you're doing. So you're forced to wrestle with the abstract data type and understand it so that you can write tests that will enforce abstract data type functionality. It also places the burden on your implementation code to prove itself against those tests. There's a tendency, if you wait until after you've written implementation code to write your tests, you end up writing tests that make your code look good. By doing the tests first, now the burden is on your implementation code to pass the tests. It also means that you have tests in place from the very moment that you start writing your production code. So right away, if there's something wrong with your production code, it will be caught, and that's going to reduce the number of bugs in your code. I cannot emphasize enough how important that is. Most of your development time is really spent chasing down bugs rather than writing new code. So if you can reduce the total number of bugs in your code, you will reduce the total amount of time that you spend on development. There's also a tendency, if you leave testing until the end of a production cycle, of a development cycle, you may work right up to the very end, the deadline for your project, and not leave yourself enough time to do good testing. So by doing your testing first, you guarantee that you have tests done, and because you're reducing those bugs and you're spending less time debugging, you more than make up for that amount of time. So it prevents you from the situation where you never end up testing your code properly.